Hi, this is Chris O'Brien. We'll give people about a minute to finish signing on, and then we'll get started. Okay, well, welcome to today's webinar. Today's topic is functional safety assessment of final elements. I'm Chris O'Brien, and I'm a partner with Exida Consulting. I've got over 30 years experience with process automation, high reliability backup power systems, and functional safety consulting. I primarily work with our OEM customers to help them implement IEC 61508 development processes and with assessments, as well as with our IEC 61511 customers or our process owner customers for implementing a functional safety lifecycle and keeping their plants running safely. So our topic today is functional safety assessment of final elements. IEC 61511 requires that functional safety assessments be conducted at various points in the safety lifecycle. A thorough and well-documented evaluation of final elements is not only a standards requirement, but also one of the most important activities that can be conducted to ensure safety, reliability, and process availability. And in this webinar, we'll take a look at a straightforward process to achieve effective final element assessments. As many of you probably already know, Exida is a global consulting firm with offices around the world. We are focused exclusively on high availability, high reliability systems, and we help our customers in a number of industries, including process automation, automotive, nuclear, and we help equipment owners, equipment manufacturers, as well as process owners. Our offerings, what we offer kind of is a pretty broad range of services and products. We offer consulting, product certification, training classes, engineering tools to facilitate the life cycle, reference materials, and personal certification. Excellentia is the leading lifecycle tool in the process industries for implementing functional safety systems. It's made up of a collection of best-in-class tools that can be used on any particular lifecycle phase, supports intelligent lifecycle integration and movement of data throughout the entire enterprise. So we have different tools that can be used as standalone tools, such as a fax tool or a LOPA tool. Our Silver tool is the industry standard, and you can use just a tool by itself, or as more and more people are doing, they're implementing an integrated suite where the data and the information from one phase of the life cycle flows and supports the other phases. So it's quite a popular tool. We also publish books and articles, and that helps do a few things. One, it builds our brand, but it also helps show what our work process is and some of the cutting edge thinking we have going on is, and documents it so people can can use it. They could come back and ask questions and challenge it, or and I think we think it helps move the industry knowledge forward. So our topics today, in today's webinar, we're going to take a look at what the objectives of a functional safety assessment are, what specific requirements there are for final elements, look at functional and integrity requirements, talk a little bit about verification and validation planning, and then we should have some time for questions at the end. So the first thing, a functional safety assessment, the objective of that is to investigate and then based on evidence to judge the functional safety achieved by one or more protection layers. So this is really, you can think of it as a validation activity to confirm that the designed protection layer is actually achieving the risk reduction or risk mitigation that you've attributed to it. Now we're going to talk throughout the webinar about validation and verification. So validation is the activity of demonstrating that the safety instrumented function and or system under consideration meets the requirements of the safety requirement specification. Verification is the activity of demonstrating at a phase level that the requirements of that specific phase have been met. And you can do that by analysis and or tests for that input and output, and you confirm that. So typically, overall, you'll develop a verification and validation plan where phase by phase and step by step you verify that that step is done correctly, and then at the end you verify overall that the system is in the correct configuration and can achieve and perform its safety function. When we look at the different steps or different typical steps that you'll find in a process plan that come before the functional safety assessment, we'll look at installation, commissioning, and then some validation steps. When we talk mostly today, I'm going to focus around functional safety assessment 3. So IEC 61511 points out 5 different points where a functional safety assessment could be conducted. The first is after the SRS is written. The second is after conceptual design, after design. And often that's tied in at the FAT. Because then you've got that system in place, or often it includes the FAT, but it would include the steps such as, confirming that the SIL verifications are correct, confirming that the different requirements are written out. FSA 3 is the assessment that occurs prior to startup. Must be done, all the equipment is installed, it's ready to go in an operational state, but the hazard isn't present yet. So that's, I think, a convenient one to think of. The concepts and techniques we're talking about, we'll see kind of build through that, FSA 1 and FSA 2. Then I mentioned there were 5 points. So FSA 4 is a periodic review for a modification. Periodic review basically on time if nothing's changing, and or if a modification is made. And FSA 5 would be before a safety system is taken out of service. So as we're getting ready for this pre-startup safety review or FSA 3, often where you're going to be installing the system. So in installation, we want to make sure the equipment is installed per the specification and drawings, and the typical activities, as with any installation, mount the equipment per instructions, install all the components, make sure the jumpers and key mechanisms are correct, make sure the grounding's there, connect the energy sources, calibrate the instruments, connect the interfaces, connect the field devices. So much of what you want to verify in the FSA are steps that are occurring in the normal installation and startup of a system. We also want to be careful and be sure we verify the environmental stresses, so heat, electrical conditions such as surge or EMI, RFI radiation are important to consider. Mechanical considerations, shock and vibration, and also fit for use or making sure there's no application mismatch, such as checking for incompatible materials. In commissioning, so now we've installed it, we've verified that it's suitable. We're going to commission the system and we're going to check for correct installation and functionality. We want to note any as-built changes. And even with the safety system, it's understood that you may have some disconnects or you may have some specific as-built activities. And you're allowed to allow that to occur, but you want to record what the as-built is and then go back and then confirm that it doesn't violate any of the requirements of the safety requirement spec. At this point, we also want to check that the installation is done per the safety manual, and we want to make it in a state ready for validation tests. So the objective of validation is to ensure that the safety instrumented system, as installed and commissioned, is ready to meet the safety requirement specification. And we can do that through, that validation can be accomplished through a combination of testing and inspection. So if we look at this kind of little flow, we have FAT, installation, site acceptance testing, site integration testing, commissioning, and we're going to do this functional safety assessment at this point prior to startup. So that would be our FSA 3. Activities that we're going to do during commissioning prior to the FSA are make sure packing material is removed, make sure all jumpers, keying mechanisms, or protective components are installed, confirm the grounding, confirm energy sources are connected and operational. Basically, we're going back and validating or confirming that those installation objectives were actually done and done correctly. So this list is essentially the same as the installation objective list, but this is a step going back and confirming. So for final elements, it's important to pause and kind of consider them in context. So often there are changes and things are going on with the logic solver, so sometimes it can take the majority of the focus, and not that that's inappropriate, but I've seen it happen where the focus has been on the logic solver, and because it's considered complex and changing, and sometimes not enough focus on the final elements. So we want to be careful about that. And essentially just checking installation of field equipment and wiring alone isn't really sufficient enough to be considered a comprehensive final element functional safety assessment. So a review of the design, the assembly, the functional test results is also necessary to have a good holistic view of that final element and confirm that it is ready to do its job. Let's look at how we can derive or flow information from the safety life cycle into requirements for the final element. So in kind of a simplified life cycle shown here, we'll have our process hazard analysis, we'll do SIL determination, write a safety requirement spec, perform SIL verification, confirm, hey, did we meet our requirements or not? If not, we go back and do some redesign. If we have, we go into our detailed design, then we'll go to FAT. Often for a final element, after verification, that's then going to drive ordering the components, the valves, the actuators, motor contacts. Like if it's a pump or a motor application, you're going to be ordering that equipment as well as the the contactors or the safe torque off equipment to control them. Then you'll have site acceptance testing, site integration testing, proof testing during the operational phase, check now and again has it been properly maintained, and ultimately decommissioned. So what information can we draw from that for our safety life cycle? So if we look at The blue side or the right side of the screen, this kind of details information we want to capture at each stage. So at the PHA, we want to capture the process information and things such as the demand rate and the proposed functionality for the system. At SIL determination, we'll get metrics such as safety, reliability, and process availability goals. The safety requirement specification gives us functional and integrity requirements. We'll expand upon those. SIL verification essentially is going to confirm that yes, we did meet our requirements, or no, we need to go back and adjust our design. FAT can be used to verify that the assembly, the integrated assembly of valve, actuator, and say solenoid for control are correct. After we install it, we want to validate the system is correctly installed. Then we're ready to run. Between 6 and 7 we're running. Periodically we're going to run proof tests, and the purpose of a proof test is to discover dangerous undetected failures. Periodically verify that we are running those proof tests and or if there's going to be a change to the system. And then finally, before we decommission a system, a final safety review. So there's key information we can pull out of the phases of the life cycle, and we want to keep that in mind as we're kind of going through the process of thinking of final element verification and validation. Now, we'll have a overall safety instrumented function safety requirement spec, and that can be decomposed. We can think about decomposing that into requirements for the sensor element, requirements for the logic solver elements, and requirements for the final element. And typical things within the final element are valve, actuator, and control device, often a solenoid or a valve positioner if it's an automated valve. If it's a motor or a pump, most cases they're going to be de-energized to trip situation, so you may be just considering the contactor there, maybe with a guided contactor with feedback, or a regular contactor. If it's energized to trip, then you're going to be considering requirements of not only the contactor working, but power being available, and also the motor or the pump working correctly. So those requirements will be decomposed or allocated out to different devices and components within each element. If we look at that safety requirement spec, and we go to the right-hand branch and think about the final element, we can talk about a few things and look at functional requirements and integrity requirements. For functional requirements, it starts as simple as what is the function, what's the function that has to be achieved, and in this case we'll talk as if it's an actuated valve for clarity. What's the function of the final element? Is it fit for application? Or making sure it's fit for application, picking the type of equipment, the material compatibility and pressure temperature range. What's the useful life? So how long does it need to run, or how many cycles does it need to support? Then there's some key things such as running torque or active torque versus break-free torque. There's some valve manufacturers that provide guidance. So for example, if the valve is going to be actuated daily or continually to move, they might recommend to say, hey, your maximum torque is 1x what the torque table says. If it's going to sit for a long period of time, say a year, the recommendation might be that you need to design for 150% of the torque in the torque table, because there's going to be a much higher break-free torque required. So those types of requirements are important to capture. Feedback and diagnostic capability, what you want designed into the system, is very important to consider at the conceptual design stage. Will you need to do a partial valve stroke test as a diagnostic? Will you want to do a bottle check or a leak check with your system? What different types of things do you think or expect to want to do? So those are functional requirements, and then there's going to be integrity requirements such as what leakage rate is tolerable, what's the closing time for the valve, uh, what failure rates or what's the target PFD average, what SIL level is a safety instrumented function, and are you going to accomplish that through using certified devices or using a proven in use approach, and what type of proof testing do you anticipate? That's another key thing that ties in with the diagnostics. Will you have online diagnostics, or will you have or proof testing? If so, what steps of the proof testing will there be, and what type of coverage will you be able to claim? And that has a big, those decisions have a big impact in the overall achieved risk reduction. So they're important to consider, document, and verify as we go through the verification phase, the SIL verification. So functionality, objectives, we want to select a valve and actuator or a motor or a pump that's applicable for our situation. Confirm material compatibility, confirm pressure and temperature requirements, and as I was talking about, are there any special requirements for diagnostics? Do you need a smart shutdown device to run partial valve stroke testing, or are you going to do an application type diagnostic such as a partial valve stroke test controlled by the safety instrumented system? And then, are there any special application requirements such as is it a slurry? Is it a cryogenic application? Is it a Coker valve? You know, so there can be very unique things that will impact the overall system. We want to capture all of those. So continuing to talk about functionality, we need to know the number of cycles or years per year and make sure we're not going to hit a wear out point, and we also need to know the number of years before we might have to change or repair the device for soft goods. So if we think of a solenoid, it could reach the end of its useful life because it has many cycles, or because we've ran it for 10 or 15 years and the elastomers need to be changed out and refurbished because the shelf life of maybe the particular components or compounds used is 10 or 15 years. Again, this new torque, the torque required of the valve when it's new or when it's in motion, we need to know. We also need to know if we expect that's going to increase over time because of buildup and or lack of use. But then we also need to understand the torque or force provided by the actuator. So we might have higher torque, or it wouldn't be unusual to have a higher torque when an actuator is brand new. And I'll use torque interchangeable with force, but a higher torque or force output when they're brand new. And that may go down over time as the seals wear and we have a little more leakage past the seal, so we can't get quite the maximum force. So that's a key thing to understand, that the actuator valve combination, that the actuator is going to be able to provide the necessary forces to move the valve when needed, but not such high forces as to damage the stem or plug by over torquing it. So that's an area that we're seeing more effort on in general in the market, and that there still needs to be quite a bit of work to do. Again, if you're going to be using diagnostics, you're going to want to consider position feedback and or diagnostic capability at the design level. Integrity requirements are going to be how well does it need to work. So the functional requirements are what is the function, what's it doing, and then integrity is and how well does it need to do it. So leakage rate is an example of how well it needs to seal. Closing time is important and on most SIFs because that, it's essentially how quickly will that final element bring you to the safe state, or if it's a motor, how quickly does that stop spinning down? Is there a lot of inertia in the motor that's going to continue to drive stuff even when you de-energize it? Similarly with the pump. So understanding those conditions are important. Sticking with our automated valve example, if we look at the things that are in there, certainly most people say, of course, there's a valve, there's an actuator, and there's a control device, and they'll typically capture that in the analysis. But in addition to that, maybe there are feedback devices. Maybe there is a need for a quick exhaust valve or a volume booster, but almost always there's going to be a mounting bracket, coupling, hardware. So those are components that need to be included not only from a verification perspective, but also from a design evaluation. Are they designed well such that they're going to perform their function? And we want to consider if we have a dual or potentially a dual acting design where the availability of pneumatic supply and hydraulic supply also has to be considered. With that with that thought process, or that pretty broad group of things to consider, it's important to take a moment then and do verification and validation planning. Because a little bit of time up front can help create a plan that when you get to your commissioning stage, you've collected a lot of evidence along the whole life cycle development or project, or, delivery of that integrated or that final element, that integrated valve assembly or other equipment. This chart kind of shows a little bit where you can grab different information, or if you're thinking about it, you can collect information at different phases of the project to support the FSA 3 as we're using as our example. So SIL verification, you need to get a bill of material and you need to get failure rates. That needs to include not just the valve, actuator, and solenoid, but also mounting adapters, bracketing, anything such as quick exhaust or volume boosters that are needed to make that final element behave or be able to provide the performance the safety requirement spec is asking for. A design review can help confirm the functional requirements are correct and validate the design of the components such as the brackets and couplings. Assembly and test, if there's a formal test procedure, which is important, you can collect that information there and that will support the FSA 3. For functional validation, that's typically going to be on site. We can definitely leverage the SAT will be on site, but the test plan could be an FAT test plan. So if it can be tested at the integration site where that's all put together, and say speed of response at given input pressures and validation of the steps before, that's very useful, because then at site you're essentially just confirming it's still working correctly and is installed properly. And then also in addition to those tests, there's requirements for documentation for FSA 3, such as the specification, so safety requirement specification, and then evidence to show that the equipment picked meets that, design verification, test results, and inspection results. So you could do all of this at the end, but if you factor that in, or you're looking at that as you're going, that makes the whole process a little more doable and a little more efficient. I want to pause a moment and talk about design. So design is an important thing. We mentioned about the breakaway torque. So there are going to be design requirements for things such as couplings or valve stems, and ensuring that you're not over torquing a valve stem. So of course the valve manufacturer is going to have a design guide. They're going to design it, but not only is there a minimum torque necessary to move the valve, there's also a maximum torque it could take without damaging the valve or the stem. Designing the couplings and the brackets for strength, and are they rigid enough? Are they sufficiently designed that they're going to do their job reliably? And then coming back once again to diagnostics, do we need diagnostics to reach our safety metrics? If so, how are they designed and how are they implemented? So it's helpful to think about the amount of rigor that a valve manufacturer or an actuator manufacturer goes through when they're designing a product. They have a requirement for a developmental life cycle where they're going to have a product requirements and they're going to decompose them into component requirements. Then they're going to do all of that design and they're going to integrate it back into an assembly and they're going to test it. And they're going to do, you know, a validation testing to prove that their design is correct, and every time they build a valve in the shop, they're going to do production testing and verify that the next valve they built works correctly. A similar thought process should go into the final element design, because if you are, you know, if it's standard and there's brackets, you know, a manufacturer has a standard integrated assembly, this rigor's probably been applied. If, as in many of the cases, you know, people are designing and putting together collections of equipment for each final element, there is design considerations and strength considerations that need to go into designing those interfacing components. And while you may not need the rigor of an OEM, you know, being completely informal or doing it based on, you know, it's worked in the past is not enough rigor for safety, for final elements going into safety systems. So this slide kind of, we were addressing or we're thinking about the systematic correctness of the design. And then with SIL verification, we're actually going to do, you know, we're going to do the modeling for the random reliability. And it's important at that point that the components that are needed to make it an assembly are included in the SIL verification calculation. So we need to include, you know, the failure rates for couplings, the failure rates for brackets, failure rates, although they are a second order for feedback switches for diagnostics. So they're not as dominant as, say, a coupling failing, but they should be considered as annunciation failures for modeling the system. So all those parts that are safety critical need to be included. Accurate failure rates are always an important thing to get. If you don't have valid failure rates going in, then you're not going to have a valid calculation or result. Sources for failure rates are valid or validated field failure studies. Safety Equipment Reliability Handbook, that's a book published by Exida, or RETA publishes data, Exida specific or Exida device FMEDAs, and silsafedata.com. So silsafedata.com lists a range of what's considered to be typically a valid range for different types of equipment. So if you don't have specific data, you can use you could use this website to get a feel. If you had data that was significantly higher, you might be being too conservative. If you had data that was significantly lower, you might be being too optimistic. So it's a good cross-check or a good place to get kind of a validation of the data you're using. There's also a requirement that for any device used in a safety instrumented function, that equipment, that those devices be selected or based on an assessment to 61508 or based on proven in use. There's another website, Safety Automation Equipment List, that lists certified devices and provides references for or links for assessment reports and certificates. So that's a good way to help collect information as some of the evidence that the design or the devices are suitable for the design, and putting it together, because that is one of the things in the FSA 3 we should be validating. We've met the SRS, we did a correct design, the SIL verification is correct, so we meet probabilistic numbers, we meet architectural requirements, we meet SIL capability requirements. Take a moment here and then talk about proof testing. This is kind of where we're going to bridge from design to practice. So definitely when we're doing SIL verification, we're going to be modeling or thinking about the proof test we're going to implement and giving it a specific proof test coverage. Here, for example, are 5 different proof tests that could be run on a ball valve assembly. You could do a partial valve stroke test, you could do a full valve stroke test, you could do a full valve stroke test at operating conditions, a full valve stroke test and a leak test, or a full valve stroke test at operating conditions and a leak test. So those are 5 different tests. I've seen them all implemented. They're going to give you different proof test coverages. So if we want to understand the effectiveness, we need a reasonable baseline for the failure rates of a device. We need to perform an FMEDA on that device with appropriate functional failure mode. So when we're doing SIL verification, we're often looking at, well, is it a safe or a dangerous failure? Is it detectable or undetectable? And that's important. When we're trying to evaluate the effectiveness of a proof test, we want to also consider from a functional perspective, if I get a failure, how does that present itself at a system level or a subsystem level? Does that failure result in excessive force being needed to move the valve? Does that failure result in a leakage across the seat? Does that failure result in a disconnect between the obturator or the ball and the stem? So we want functional failure modes, and then depending on our proof test, we're going to assign a coverage, and finally we're going to say, well, what do we detect with a diagnostic, and what do we detect with a proof test? So this is an example of a floating ball valve where the failure rate, so the dangerous undetected failure rate down here is 575 fits, but that breaks down, if we look at it from a functional mode, that breaks down between failures that are going to require excessive force to move the valve, failures that are a loss of drive, and failures that are leakage past the seat. Then what we can do when we have that, we can say, if we take our 5 proof tests, so over here, this is the most complete. We're going to close the valve at operating conditions. That's going to be maximum force on the valve. It's going to confirm, if we can move it in that condition, we should be able to move it. We're going to check for a leak test. So if the ball has become disconnected and doesn't close, we'll find that. Or if we have a leak across the seat, we're going to find that. So in this case, this proof test 5, we're finding 99% of all possible dangerous failures. That's good. Maybe more than you need in your application. You might not need that degree of coverage to meet your safety reliability metrics. It may not be practical to do. So then you might say, well, I might do a different test. Maybe I'll just do a partial valve stroke test. And the standard doesn't say what test you have to do. The standard basically says you need to, model it correctly. So in that case, with a partial valve stroke test, you're going to find 60% of the binding failures, and you won't find any loss of drive or leakage failures. And so you could go anywhere from a dangerous detected failure rate of 201 to 568, depending on what proof test you use. And that's, that is, there's no right answer. Really, the right answer is the one that provides you the safety reliability and process availability you need. But it is important to consider that not all testing is the same, and you want to model it to reflect what you're actually doing. You also want to be careful, like this example is a specific example for a floating ball valve in a close-on trip application. If it was a tight shutoff application, the failure rates would be different, and if it was a fail-open application or open-on-trip application, it would also be different failure rates. So this is a good technique to use, but you want to be sure you take the time and model your specific system. Now, we've kind of gone through the verification step, and now we're going to start getting into the installation or the validation or verification steps leading up to verification of the assembly leading up to the Functional Safety Assessment 3. So, should you do an FAT or should you do a witness test of the integrated valve assembly? Well, probably depends. Here's 2 pictures that show kind of dramatically different, let's say, levels of risk or levels of getting something assembled incorrectly. So if you're buying kind of a standard assembly from an OEM, they've probably got pretty good procedures in place. They can probably give you test results of how they tested the integrated assembly. They've designed the components, so the bracketing and the coupling is probably sufficient to do its job. Doesn't mean you shouldn't ask for that evidence, but you might not have to go to the point of witnessing it. Whereas if you're getting kind of a specialized assembly from an integrator, you might want to witness that and do some confirmation steps before that integrated assembly ships. And the same could be, you know, there could be dual acting valves where you've got a hydraulic skid that goes as well. There can be pumping systems or, you know, motor systems that you want to you know, that come with their own, you know, electrical panel. So depending on the complexity of what your final element actually is, doing an actual factory acceptance testing before equipment ships can be very beneficial, and if done properly, it's going to generate documenting, kind of confirming that how the integrated assembly or the pumping system or the, you know, MCC is correct and suitable for service. So don't have to do it, but it can be a pretty useful technique for unique solutions or, you know, special systems. We take a look at the kind of the next validation activity. We want to do these validation activities, so that's down here in this bracket. So we've done our FAT. We may or may not have done an FAT. The stuff is shipped. It's been installed at site. Now we want to start to validate. At validation, we want to confirm that the full functionality is available and working properly, and that the requirements of the SRS are met. That the equipment is installed per manufacturer's instructions, it's installed per the safety manual, the periodic testing that needs to be done is documented and available, all the previous safety lifecycle documents that should be available are available and complete, and it's a pretty good idea for these types of steps to have a checklist. Those are good things that can help make sure that from project to project or person to person, things aren't forgotten. The validation test of the SRS functional requirements will include making sure the definition of the safe state is there, what the process inputs, trip points, operating range are, the outputs and their actions, relationships between inputs and outputs, and then, you know, specifically some final element things that are maybe of more interest are, you know, is the system energized to trip or de-energized to trip? If we needed them, do we have manual shutdown means or bypass? Does the final element go to the correct state on loss of power to the safety system? Are the response time requirements met? If there's an overt fault, does it behave as we expect? Is there a requirement for local reset, such as a latching solenoid, that you're going to require somebody to go out and inspect the site before it goes back and running? And what is supposed to be available as an operator interface, and is it available? All that should be captured, or the results of that should be captured in a validation test report. The checkout forms were done, recording what tool and equipment is used, including when it was calibrated, test results, what the specification was, what the criteria to accept or to pass the test was, what version of the safety system is there, probably build number, discrepancies between what, when you did the planning, you expected to see and what you saw, and then some proactive decision, or I would say positive decision, that those discrepancies are reviewed and accepted, or if they're not accepted, go back, you know, and that the corrective action was done, and finally a sign off and acceptance. So, you know, that's going to serve as a basis, or a good basis, for the output. So we're going to review that all commissioning and pre-startup activities were completed, maintenance and operating procedures are in place, personnel have been trained, bypass functions are removed and the system is in its normal position. Isolation valves are set in their proper position. All test materials are removed and all forces are removed. And at that point, then you're ready for startup. So at this point, enough information, everything should be done that the FSA 3 can be completed. And that's kind of the objective. One thing I want to point out is that the installed assembly does need to be inspected and validated, and we can use a combination of tests and inspections and evidence that can be collected from the OEM at integration and at commissioning to create that evidence that everything that was necessary to be done has been done. So that takes us up to operations. We start up and we're running. And just an important thing I want to emphasize is that proof testing is then the thing that happens for the rest of the life of that system. So maybe it takes 6 months or a year to design and build and install that system, but then it's going to run for 15 or 20 or 25 years. That periodic proof testing is the key to ensure that safety reliability is maintained. So if that's not done and not done in an organized way, you don't achieve the operational phase of the life cycle. So proof testing needs to be a formal, structured process. Data must be collected and compared with the information that was used to model the SIFs. Any discrepancies found must be addressed. Hey, a discrepancy could be we're not actually testing it as often as we said we would. We're experiencing higher failure rates of the equipment than we thought, or we're experiencing a higher demand rate. And another issue is often proof tests are not fully executed. And I've worked with customers on projects where they had two process trains. They had a large safety ball valve in each train. Within the first month of commissioning, they sheared the stem off of each ball valve, and there's a sign of, hey, maybe the breakaway torque was more than the people who integrated the assembly thought. Or the stem strength was lower than they thought, so they put an actuator on there large enough to break it free, but it was the breakaway torque was higher than the shear torque that the stem could take. So those are real issues that we see that exida sees with their clients often. So capturing those things and those types of failures are very important to feedback and correct the loop. And if you don't do proof testing at the frequency you model or at the effectiveness you model, you're really going to wind up overestimating your achieved safety reliability, because over time, this basically the instantaneous probability of failure on demand is shown by this. So if we extend our intervals, we're going to have a higher average probability of failure on demand. Or if we use a less effective proof test than we model, we're also going to wind up with a higher probability of failure on demand. And I've seen, depending on what actually is done, it can be anywhere from a factor of 7 to 10x higher probability of failure on demand. So you can kind of think like you might be losing a whole SIL level by not executing the operations phase per your design. So that's an important thing to keep in mind. And that would come in with our FSA 4 or the FSA 4 reviews. If you're making a change to the system, validating it again, and or if it's a very stable system, you still want to periodically say, check, are you doing proof tests? Check your your actual failures. So kind of in summary, the need for a thorough, effective, traceable, and practical functional safety method, functional assessment method is necessary. With careful planning and doing it throughout a project life cycle, that can be facilitated if we ensure we have accurate and complete requirements when we write them, and we keep them up to date if things change. We flow these requirements down to devices such as valves and actuators or motor contactors, as well as the components necessary to make all of those things work together. And we implement a well-constructed verification and validation plan that captures information at its most convenient step. Because frankly, if you can do a stroke test at the valve integration house, it might be quite a bit simpler than doing it on site. So, that planning out the V&V activity can make it much more possible to get, much more possible and practical to get good functional safety assessments of those final elements. So I think that's my last slide. So let's, we've got some time, so let's take some questions if we have any. All right. So this morning we had like 50 questions, so we'll wait for some here. Okay, so one question, availability of failure rates for couplings and brackets. So that is an important thing, and some manufacturers include that in their FMEDA report and their safety manual. I don't think I'll check, but I don't think we've listed that yet on the SIL safe data, so I think that's something that we can add as some components on there. So we'll do that. Some questions about coverage for, say, a motor, examples for motor proof test coverage. So if we looked at a motor or a pump, so often for those, it's going to be the contactor if it's a de-energize application. So if you kind of de-energize and then confirm that the final element or the pump or the motor is stopped, then you can get up to a 99% coverage. So here's another one. Just trying to expand it. Oh. So is there standard components that needed to be included in a valve assembly? So I think that as a minimum, you obviously have you would have the valve, the actuator, the solenoid, but pretty much you're going to have a bracket, couplings, and at least mounting hardware. So I think that we should be considered that those should be, make sure somehow that's addressed in the SIL verification model. And just a general question. So we will send the presentation out to everybody, and we will send out the questions with answers as well. We're going to combine both webinars. We did it 2 different times, and we'll send that out so everybody will get the info. How often do you determine, how do you determine how often proof tests should be performed for various devices? That, there's going to be 2 things that go in, well, let's say there's 3 things. So one is there's going to be a plant operational philosophy that we do tests once a year, once every 6 months, or once, say, every 3 to 5 years. So there's going to be a plant desire for the frequency. There's also going to be a requirement that that proof test is run at least twice as often as the demand on the safety system, because we want to model these things in low demand. We want to be able to take credit for diagnostics as well as proof tests. So it's going to give us the best safety reliability. So one is a plant desire of a test frequency. The second is at least twice as often as the expected demand on the system. And then the third thing is going to be, are you achieving your safety, your desired risk reduction with your desired proof test frequency? So if you're not, you may have to, if you're not, say, achieving your risk reduction, you either have to do the proof testing more often, increase the effectiveness of the proof testing, and or add redundancy to the system. So it's a kind of an iterative process where you're looking at those variables. So how can the probability of failure on demand be determined for a spring-opposed pneumatic actuator? So the FMEDA, an FMEDA would be performed, and there are failure rates for the different parts in there, so such as a spring, a piston or a diaphragm, a housing, cylinder housing. So let's say it's a piston, a pneumatically actuated piston actuator. The safe state typically is vent the energized pressure and let the spring close it. So you would do, an FMEDA would be done, and that would generate those failure rates. Final element usage factor. Should conditional modifiers for use, for example, opening a train only 20 hours per month, be applied at the local level or at the final element's PFD contribution? So I would say that if it is, the risk is only there 20 hours out of the month because it basically isn't applied, I would put that into the LOPA, because I wouldn't, the probability of failure, if I'm understanding the question correctly, so I'm envisioning a SIF that only needs to be functional when the train is open or in use. So that SIF is going to have an overall probability of failure, and the PFD is the average probability of at an instant of time that it's not available. So that SIF isn't changing, but it only needs to work 20 out of, however hours there are in the month. So I would put the modifier as a use factor. I put that as a modifier, or a use factor or a time at risk factor in the LOPA. Sorry, now we're diverging a little into LOPA, unless for some reason the hazard's only there, or the hazard is much more probable when the train's in operation. Then you get into some thoughts there, like, so for example, hey, it's only at risk during startup, but we have 3 people out by the turbine at startup. So you go, well, okay, it's only at risk, but we're putting all our people there, and we know we're going to start it, at least once a year. So, you still have 3 people at risk. So that's a separate discussion. Are there checklists available for the different FSA stages that can be shared? I will check on that, and if we don't have them, we'll put some together. We're releasing a second edition of our valve book in the next couple months, and I think they're going to be in there. So I'll take an action on that. Can your diagnostic coverage be used to perform proof testing, or is proof testing more of a manual test by a person? Okay, so that's a good question. Probably should have clarified. So a diagnostic in IEC 61508 or IEC 61511 is an automatic function that will detect and can take action on a failure. So to be a diagnostic, it must run much more frequently than the demand. So we could think, we'll start first with a smart transmitter that runs all kinds of background diagnostics. It notices there's a memory correction or there's a data mismatch. It says, I'm no longer healthy. I'm going to set my current output at 21.5 milliamps. That would be an internal diagnostic to the transmitter that puts the transmitter in a predefined, safe state. A proof test would be a test run on that transmitter to find something that the transmitter can't find itself, such as a frozen output. Maybe it actually would know it's got a frozen output, but it can't communicate that to the system because the output's frozen. In a valve, a partial valve stroke test could be done as a diagnostic. So let's say you had a smart positioner, or you had the safety logic solver configured that once a week you were going to command that valve to move 10%, de-energize the solenoid, within X milliseconds or X seconds, it should move that 10% and trip. You could run that, once a week, once a day, once a month, and you're going to find, basically, at least part of those excessive force failures. In that case, that would be a diagnostic. If it's run automatically, the system knows it runs, and it can take an action such as, if it's a 1 out of 1 non-redundant system, you've got, when you model it, you have the mean time to restore. So you do have time to put another mean safety measure in place, or if it's redundant, you can degrade from a 1 out of 2 vote to a 1 out of 1 vote, treat the failed system, or ignore it. So you can, so diagnostic coverage is going to be really, do we classify it as dangerous detected or dangerous undetected? And a proof test could be semi-automatic or purely manual, and it's typically run at a less frequent time. So a diagnostic must be automatic, and the safety system must be able to take action without a person. A proof test can be automatic, semi-automatic, or manual, but you don't have to take an action. So I hope that helps clarify that. All right, I think that's our questions, and that's kind of working out perfect timing. So we will send the questions and answers out, as well as the ones from this morning, to everyone. And as always, if you have any questions for me or anybody at exida, please just send us an email, and we'll get back to you. So thank you for attending, and have a safe day.